All right, this is going to be a short introduction to nuclear radiation. And we've already talked a little bit about kind of some of the stereotypes and images in pop culture that we think about when we think about this. But it really is, in a lot of ways, not quite as dramatic as you think it might be. So we are going to list these things in order of least harmful to most harmful. So I'll have you label least harmful up at the top, down to the stuff that can really kill you on the bottom. Okay, so the first particle that we're going to look at is the least harmful, one of the most prevalent, and we call that particle the alpha particle. If you've ever read Brave New World or anything like that, your Greek letters will serve you handy in what is to come. So an alpha particle is the biggest piece of nuclear radiation. You'll also hear this referred to as types of nuclear decay. So as you are kind of listening and reading and learning about this over the next several days, just know that when you hear those terms, you can kind of use them interchangeably in your head. So some things to know about alpha particles is that they are positively charged, and by atomic standards, they're actually rather hefty. They consist of a helium nucleus, and it's just the nucleus. There are no electrons, which is why it's positive, right? If it's a nucleus, there are protons and neutrons, no electrons, so you have the positive and the neutral pieces, no negative pieces, so that's why you end up with a charge. So the other thing to note about alpha particles is that they come mainly from the sun, is where we see these. They come from the sun, and they're emitted when an atom is trying to become more stable. It emits an alpha particle in order to stabilize its nucleus. For the symbol, you're going to see two different ones, and I'd like you to be comfortable with either. The first one is in a format that should look familiar with. We have 4, 2, He. And if you remember, the 4 is in the position of the mass number, and the 2 is in the position of the atomic number. So that's kind of a review from our last unit. The other symbol that you'll see with alpha radiation is that little guy. In my head, when I draw it, I'm like, oh, it's a Jesus fish. But if that doesn't mean anything to you, it's the Greek letter for alpha. And so those two symbols you'll see, I'd like you to kind of be comfortable with both. The final question is, does it change the identity of the element? Let me talk a little bit about that. What this column means is, does emitting this particle change the number of protons and essentially make it a different element? So if you look at what an alpha particle is made of, it is a helium nucleus. It's 2 protons and 2 neutrons. So does emitting it change the identity of the element? And the answer is yes. Yes, it does. And you will experiment with that later on. Okay, the next letter in the Greek alphabet, if you, like I said, if you keep up in Brave New World or just know this off the top of your head, the next letter is beta radiation. Beta radiation is a little less common. It's smaller. What I want you to jump over here with notes, beta radiation is actually negative in charge. And it's very small. It's the equivalent of an electron. It's not an electron technically, and this is where we have to hold hands and walk down the path of some kind of quantum chemistry, but it is like an electron, but it comes from the nucleus. But it's not an electron, so just roll with me on that one. We said over here it does have a negative charge, and its symbol looks like, and to the best of your abilities, you can draw this. It looks kind of like a capital cursive B with a little tail hanging off of it. Because it is the equivalent of an electron, it does not change the identity of the element. In other words, you can spit out a beta particle and it'll still be the same element. Something I forgot to mention for both alpha and beta radiation is what we can do to protect ourselves from these things. With alpha radiation, like I said, it's pretty big. A helium nucleus is pretty hefty. It is a large form of radiation, which means we have some built-in protectors. You were born with one. It's your birthday suit. Your skin can actually stop alpha radiation from going into your body. So whenever you get a sunburn, in part, that is your body's reaction to protecting you from alpha radiation. For beta radiation, you need to go a little more deliberate. Beta radiation is small enough so it can technically penetrate your skin. So you need something like clothing to stop it, or paper very often, things like that. Going down the list. Okay, so back over here. So alpha is the least harmful. Beta is next. Next up, and I like this one. This isn't a Greek alphabet one, but I like it because it sounds very science fiction-y for all of my sci-fi fans out there. It's called positron radiation. And again, you're not going to have to know a lot about positron radiation, but it is kind of the shadow cousin of beta radiation. They're kind of two sides of the same coin. So things that are true about beta radiation, for the most part, are also true about positron radiation. They are stopped by the same things, like clothing or paper. It, however, based on its name, you can probably guess that it has a positive charge. So it's like an electron, but it comes from the nucleus, but it's not a proton, and it's positive. So again, just kind of roll with me on this one. I just want you to know that like there's a lot of different types out there. It does come from the nucleus. Now, how we distinguish between these two, between beta and positron, is we stick a little positive on there to show that it is not beta radiation, but it's very, very similar. And just like beta radiation, we will say that for that column right there. The final one that we're going to look at is the most harmful, and if you're a comic book nerd like me, this one shows up a lot. The last one is gamma radiation, and technically this is not even a particle. We're going to say gamma rays. This doesn't have a mass, it doesn't have a charge. This is pure energy, and that is what makes it so dangerous. This can pass through your skin, it can pass through clothing, and it doesn't really discriminate in terms of where it travels. So gamma radiation is the most dangerous. Because it is pure energy, it has no charge. So unlike an alpha particle, which is kind of this big, heavy protons and neutrons, gamma rays is just pure energy. The symbol, you can do the best you can with it. The symbol actually looks kind of like a cursive lowercase y. This is the Greek letter for gamma. And similar to beta and positron, it doesn't change the identity of the element that it's being emitted from. So if you start out as lead and you emit gamma rays, you will end as lead as well. To stop it, you do need a little bit more than, like I said, clothing or skin. You need something like, let's see, generally it's thought that 6 feet of soil can stop it. So that's why if you ever hear about people digging underground bunkers to protect themselves from the nuclear radiation holocaust, very often that's one of the reasons, is you need a lot of earth between you and gamma radiation if you want to stop it. You can also use quite a bit of lead. You heard about when you go to the dentist and you get the lead apron put on you. It's not because they're blasting you with gamma rays, but because lead is a very dense metal, and so it's able to basically put up enough of a barrier to block things like that. So here are the 4 types of radiation. We are going to spend most of our time thinking about alpha radiation in the next little bit. But again, going least to most harmful, alpha, beta, positron, and gamma. And like I said, the alpha particle is a helium nucleus stopped by your skin. Beta and positron are kind of 2 sides of the same nuclear radiation coin. And then gamma rays are the gonna kill you part, where it's pure energy. You don't want to mess with it, and you need a lot of something in between you and the source of the radiation if you want to be protected from it.